Things get more complex when you're trying to fashion a rule for the introduction of the universal quantifier. The problem here is, suppose we have phi A and we want to go to for all x phi x. Well, we only have one instance of a phi here. But that doesn't mean that we can reason from the one instance to everything being that way. So if I say LeBron James is tall, that doesn't mean everyone is tall. So how do you go from a specific instance to a universal statement? A first pass would be to say, well, we can go from phi A to for all x phi x as long as we have derived phi A for every constant. That would be easy enough if your domains only had three things in it. Say if we were only talking about the three items on my desk. If all three items on my desk can be said to be a book, A is a book, B is a book, and C is a book, well, as long as there's only three items in that domain, then we can say all the items on my desk are books. But in logic, we want to deal with domains that are much larger than that. And in some cases, infinite. So in our language, we allow for an infinite number of individual constants. That's not going to work. We need to keep derivations finite because no one can actually go through. We don't have an infinite mind. No one can actually go through and perform an infinite derivation. So what we need to do is say we can take the universal generalization only if all of those specific derivations could, in principle, be made. We can't derive them all since there could be infinitely many, but if we can say in principle the infinite derivation could be made, then we have what we need. That's true if for all x, phi x is derivable from some constant A, which may be said to be arbitrary. The thought here is that we need to introduce some important restrictions on our use of the introduction of the universal. We need to take care, in short, that the instance A is arbitrary. If A is arbitrarily selected, then we can make a universal generalization. If our statement on L1 didn't depend on the specific choice of A, then we can move to a universal statement. Intuitively, think about it like this. If you are trying to get a representative sample, what do? Well, if you want to know what everyone in the United States thinks about some topic, say you're creating a poll, you can't just say, I'm going to ask all of my friends, because your friends, that's a biased group, right? You haven't arbitrarily selected the group of people that you are polling. You need to take care to make sure that the people that you're polling are arbitrarily selected so that you get a diverse perspective. The idea is similar here. We need to make sure that A is arbitrary, and then we can move to the universal quantification. So the two provisos you see here are geared towards making sure that A is arbitrary. The first one is that A cannot occur in the formula phi x, and the second one is that A cannot occur at the top of a box containing L1. In other words, A cannot appear in any assumptions which have been made previously and which have not been dropped at that stage in the derivation where we're trying to draw the universal generalization. So let's go into more detail on each of these provisos. The first proviso rules out derivations like this one. We know that this is a false derivation. What's happened here? This says something like, let's say Anne loves herself. Anne loves Anne. Right? Knowing that Anne loves herself doesn't allow you to say that Anne loves everyone, which is what this says, right? If we didn't restrict ourselves to this proviso, then we'd be able to just go from the statement that Anne loves herself to Anne loves everyone. And that's wrong. Why is that wrong? Well, A appears in phi x, right? Phi x is RAX, and A is in RAX. So this proviso rules out derivations like this unwanted one here. Here's an example of the kind of inference that the second proviso rules out. Suppose someone reasoned that if Anne is American, then everyone is American. Now that's ridiculous. There's a perfectly coherent model of the situation in which Anne is in the set of Americans and Bill is in the set of Italians. So not everyone is in the set of Americans. And that's obvious, right? But we need this second proviso. Why do we need the second proviso to rule out that kind of erroneous reasoning? Well, we have a proof of it otherwise. So here we have the conclusion. Anne is an American. Arrows, everyone is an American. What happens here is that A is an assumption that has not been withdrawn or dropped at the stage when we want to make the introduction of the universal. We've just gone over two mistaken derivations using the universal introduction. Now let's go over a good one and show why it doesn't run afoul of the rules. Suppose we wanted to derive this statement from no premises, which indeed is a theorem of logic. How might we do that? Well, we're trying to prove a universally quantified arrow statement. We first want to derive a arrow statement and then move to the universalization of that. So how do we derive arrow statements? As always, we need to assume the antecedent of the arrow statement and then derive the consequent. So we're going to assume not fx, but a specific instantiation of the antecedent. That allows us to derive fc or gc using our introduction of the disjunction rule. Well, that's enough. What we've got is the antecedent leading to the consequent. So we close off our assumption and we write the arrow statement using the introduction of the arrow rule. Now we move to the universalization. We introduce the universal quantifier and we replace all of the instances there with x rather than c. The point here is that line 3 follows from lines 1 and 2, no matter what we picked for the constant here. We have c here, but that didn't matter. We could have put d, e, f. This could be talking about LeBron James. It could be talking about Dwight Howard. It could be talking about Harden. Doesn't matter what we chose here. The reasoning follows. So that we're justified in this step 4 here, introducing the universal quantifier. Notice C here is present in one of our assumptions, and it's also present in the formula that we're trying to universally quantify. But it doesn't run afoul of proviso 2 because the C in the assumption is already closed off. We've discharged that assumption. It's no longer an open assumption. The rule for the elimination of the existential quantifier is similar in that we need some restrictions or provisos to make sure that that rule doesn't go astray. What is the elimination rule for the existential? Well, it's when you have an existential quantifier on a line and you want to take that existential quantifier away. You need two ingredients in order to use the elimination of the existential rule. The first ingredient is an existentially quantified statement, as on line L1. The second ingredient is a statement of this form. Phi with x replaced by a implies some other formula psi. If you have both of those, you are then able to write psi all by itself on another line. It's kind of like the elimination of the arrow statement, but a little bit different as well. But notice, we can't just do this as simply as we'd like. Suppose we have, there is something that's a fish, therefore Kyle is a fish, right? That doesn't work. Just because there is something that's a fish doesn't mean we can say of any arbitrary constant that it's a fish. The only thing we know is that there's something somewhere that satisfies the formula phi. But we have no right to assume which thing it is when all we have is an existentially quantified formula. So in order to make sure that our individual constants are arbitrary, we're going to use the same provisos as we did in the prior rule, but we're going to add an additional one that A cannot occur in psi. Without that third proviso, we could reason like this. We could say there is a fish Therefore, Anne is a fish. But that's just bad reasoning. So how do we get a proof of that, and how does that violate the third proviso? Notice we can use our arrow introduction rule. We assume FA, and then we use our repetition rule to repeat FA. That means FA leads to FA, so we can use the arrow introduction. FA implies FA. Now we have everything we need in order to use the elimination of the existential. We have an existential statement on line 1, and we have an arrow statement with A in the antecedent on line 4. Well, according to this, that means we can write the consequent of the arrow statement on a new line. But we violated proviso 3 here. Notice, proviso 3 says A cannot occur in psi. But here A does occur in psi. So this third proviso is blocking us from the faulty reasoning of being able to say, look, there is something that's F. Therefore, whatever old thing I want is F.